Hello there. Find a comfortable position. Let your shoulders drop. Let the tension in your jaw soften. You don't need to hold yourself together right now. The universe is large enough to hold you. Tonight, we are going somewhere very far away. Not in the way that feels urgent or alarming, but in the way that a slow, deep breath feels. Tonight, we are going to the Andromeda Galaxy. Pass. Tonight, we are going to the Andromeda Galaxy, 2.5 million light years from where you are lying. A place so ancient, so immeasurably vast, so quietly extraordinary, that simply knowing it exists is enough to let everything else go. Andromeda is our nearest galactic neighbor. A spiral of light spun out of gas and gravity and time. It contains roughly 1 trillion stars, perhaps more. It is moving toward us, slowly, the way a tide comes in, and in 4.5 billion years, it will merge with our own Milky Way in one of the most beautiful and gradual collisions the cosmos has ever staged. But tonight, there is no rush. Tonight, we will explore 100 of the most calming, most wondrous, most quietly remarkable facts about Andromeda Galaxy. Its ancient stars, its satellite worlds, the sleeping giant at its center, and the long, unhurried dance it shares with our own home galaxy. There is nothing you need to do, nowhere you need to be. The stars have been burning for billions of years and will continue burning long after tonight. You are safe. You are small, in the most comforting way imaginable. And the universe has never once asked you to be anything other than what you are. Let's begin. Long before telescopes, long before the word galaxy existed in any human language, long before we understood that the faint, smudged light in the autumn sky was not a cloud, not a remnant of something local, but an entire second universe of stars, Andromeda was already there. It has always been there, and there is something deeply peaceful about that, about the idea that no matter what has happened in human history, every war, every discovery, every sleepless night, a galaxy containing 1 trillion suns has always been quietly visible from our world, if only we knew how to look. Andromeda is the closest large spiral galaxy to our own Milky Way, sitting at a distance of approximately 2.537 million light-years from Earth. That number is almost too large to hold in the mind comfortably, and perhaps that is part of why it soothes. It loosens the grip of small things. A light-year is the distance light covers in an entire year, traveling at roughly 300,000 kilometers per second. Light is the fastest thing in the known universe. And even at that impossible speed, the light arriving in your eye tonight when you look toward Andromeda left its source 2.5 million years ago. At that time, our ancestors were stone tool-using hominids walking across an ice-trimmed African savanna. The light you see has been traveling since before Homo sapiens existed. It crossed all of recorded history without stopping, and it reached you tonight, now, as you drift towards sleep. Andromeda bears the astronomical designation M31, the 31st object catalogued by the French astronomer Charles Messier in 1771, as part of his famous list of nebulae and star clusters. Messier was not looking for galaxies, he was hunting comets, and Andromeda annoyed him by resembling one, a soft, unfocused smudge that didn't move and couldn't be dismissed. So he catalogued it, not knowing what it truly was, simply to avoid confusing it with his real quarry. There is something gently humorous in that. The most significant galactic neighbor we possess was, for a time, merely an inconvenience on a comet hunter's list. The universe had arranged this astronomical treasure in full view of human eyes for centuries, and we initially noted it down as something to be ignored. M31 has since become one of the most studied objects in all of observational astronomy. The Andromeda Galaxy has been visible to the naked human eye for as long as our species has had eyes. Persian astronomer Abd al-Rahman al-Sufi documented it in 1964 CE in his landmark work, Book of Fixed Stars, describing it as a small cloud. For centuries before that, the Lady Appreciation says, describing it as a small cloud. For centuries before that, the Lady Appreciation says, describing it as a small cloud. For centuries before that, the Lady Appreciation, 1 centuries before that. The peoples of the ancient world would have seen it without knowing. A faint, oval smear of light sitting in the constellation of Andromeda on clear, moonless autumn nights, especially in the northern hemisphere. Indigenous astronomers across cultures noticed it. Bedouin navigators likely used it. It appears in the records of medieval Islamic astronomy as a reliable fixture of the sky. And yet, its true nature, that it was a billion times over collection of suns, an entire galaxy, a peer of our own, would not be understood until the 20th century. For all that time, it simply waited. The conclusive, civilization-reshaping discovery that Andromeda was a galaxy in its own right, and not a nebula within the Milky Way, came in 1923 thanks to the meticulous observations of astronomer Edwin Hubble. Working with the 100-inch Hooker telescope at Mount Wilson Observatory in California, Hubble identified a specific class of pulsating stars called Cepheid variables within Andromeda. Because Cepheid variables have a known relationship between their brightness and their pulsation period, they can be used as reliable cosmic measuring sticks. By calculating how faint the Cepheids in Andromeda appeared compared to how bright they should be, Hubble could estimate the galaxy's distance. His results placed Andromeda far, far beyond the edges of the Milky Way. In a single observational moment, the known universe expanded by an almost incomprehensible degree. The cosmos went from being our galaxy to being a place of billions of galaxies, and Andromeda was what opened the door. Andromeda is classified as a barred spiral galaxy, though its bar structure is relatively modest and less pronounced than the bar within our own Milky Way. Its overall shape is a grand, sweeping spiral, immense curving arms of stars, gas, and dust fanning outward from a dense, luminous central bulge. Seen from outside, it would be breathtaking, a flattened disk of pale blue-white stars set against the deep and permanent black of intergalactic space, its arms tinged with the pink of star-forming nebulae, its core glowing warm and amber with the light of older, more settled suns. Because Andromeda lies at an oblique angle relative to our line of sight from Earth, tilted about 77 degrees from face-on, we see it as an elliptical smear rather than a face-on pinwheel. But tilt it just slightly in your imagination, and the spiral arms emerge, slow and majestic, curving outward like a slow exhale. Andromeda is estimated to contain somewhere between 800 billion and 1 trillion stars. The uncertainty in that range is not a failure of science, but a reflection of genuine difficulty. Counting stars in a galaxy spanning over 220,000 light-years requires statistical modeling, careful photometry, and a great deal of humility before the numbers. 1 trillion is a figure Our minds were not evolved to feel. But try this. If you were to count one star per second, without pause, without sleep, it would take you over 31,000 years to count 1,000,000,000,000 of them. Andromeda holds that many points of light. Each one is a sun. Many of them are larger, hotter, and more radiant than our own. Some are ancient red giants burning the slow, dim embers of their old age. Some are young and blue and fierce. They are all, at this moment, burning quietly, ceaselessly, across 2.5 million light-years of darkness. Despite containing roughly twice as many stars as the Milky Way, Andromeda is actually thought to carry less total mass. This might seem paradoxical. How can more stars mean less mass? The answer lies in dark matter. Galaxies are not defined only by their visible stars. They are also shaped and held together by vast halos of invisible mass that neither emits nor reflects light. Astronomers believe the Milky Way possesses a particularly massive dark matter halo, which accounts for the bulk of its gravitational weight, even though it contributes nothing to its visual luminosity. Andromeda, by this measure, is the lighter sibling, richer in stars, but sitting within a somewhat less massive dark matter envelope. The Milky Way's total mass is now estimated to be comparable to, or even slightly greater than Andromeda's, a reversal of what astronomers assumed for decades, and a humbling reminder to never assume we have fully understood anything Andromeda spans an extraordinary distance. Its disk alone extends for roughly 220,000 light-years in diameter, more than twice the estimated width of the Milky Way, making it the largest galaxy in the local group by physical size. Its extended outer halo of diffuse stars and gas pushes that boundary even further, potentially stretching to over 1,000,000 light-years in diameter if the full stellar envelope is included. From our vantage point on Earth, even though it is invisible to the naked eye beyond its bright central core, the full angular extent of Andromeda's outer halo covers a patch of sky nearly 6 times the width of the full moon. If it were bright enough to see in full, Andromeda would not be a pinprick of light. It would be an immense, diaphanous oval draped across the autumn sky, a second presence, quiet and vast, sitting right beside us. Andromeda is a member of a gravitationally bound collection of galaxies known as the Local Group, a family of roughly 54 confirmed galaxies spread across a region of space approximately 10 million light-years in diameter. The Local Group has 2 dominant members, the Milky Way and Andromeda. They are the heavyweights of this neighborhood, each holding court over their own collection of smaller satellite galaxies, which orbit them the way moons orbit planets. The remaining members of the Local Group are modest in scale. Dwarf galaxies, irregular systems, small ellipticals, but they add texture and depth to the local cosmic environment. The Local Group itself is a relatively quiet, average-sized cluster by the standards of the universe, embedded within the much larger Virgo supercluster. We are not at the center of anything. We are in an ordinary corner of a medium-sized room in an incomprehensibly large house. At the very heart of Andromeda sits a supermassive black hole with a mass estimated at approximately 100 to 140 million times that of our Sun. For comparison, the supermassive black hole at the center of our own Milky Way, known as Sagittarius A, has a mass of roughly 4 million solar masses. Andromeda's central black hole is therefore somewhere between 25 and 35 times more massive than our own galaxy's central singularity. It sits anchored at the core of Andromeda, like a silent engine, its gravity shaping the orbits of stars for tens of thousands of light years around it. Unlike some of the most dramatic black holes we have observed elsewhere in the universe, Andromeda's is currently in a relatively quiet state, not actively accreting large amounts of material, not producing the blinding jets of an active galactic nucleus. It simply holds court, massive and still, a sleeping thing at the center of a sleeping galaxy. Andromeda is approaching us. Right now, as you breathe, as the seconds pass, the Andromeda Galaxy is moving toward the Milky Way at approximately 110 kilometers per second. That is fast by everyday standards, yet across 2.5 million light-years, it feels unhurried. At this rate, the eventual collision and merger of our two galaxies is expected to begin in approximately 4.5 billion years, with the full merging process taking another couple of billion years beyond that. What emerges is predicted to be a large elliptical galaxy, sometimes poetically nicknamed Milky Way by astronomers, a blended world of stars from both families. It is worth noting that galactic collisions are not violent in the way one might imagine, because stars are so vastly separated even within a galaxy. Individual stars almost never actually collide. The drama is gravitational, a slow, majestic reshaping of two spiral worlds. Andromeda's light-gathering power, the sheer number of photons your eye can collect from it on a very dark, clear night, makes it the most distant object visible to the unaided human eye on Earth. On nights when conditions are ideal, far from city lights, under a sky of profound darkness, it appears as a soft, elongated smudge in the constellation of Andromeda, just above and to the right of the Great Square of Pegasus. Ancient and medieval observers who noticed it had no framework to understand it. They called it a cloud or a nebula, words that simply meant something hazy, something without a sharp edge. And in a poetic sense, that description still works. It is a cloud of 2.5 million years of traveling light, arriving softly, without urgency, into the dark adapted eye of a curious mammal standing on a small rocky planet, looking up, wondering. The name Andromeda comes to us through Greek mythology, specifically from the story of a princess named Andromeda, daughter of Queen Cassiopeia, who was chained to a sea rock as a sacrifice and later rescued by the hero Perseus. The constellation that bears her name traces a rough figure of a woman with her arms outstretched, and the galaxy sits close to her right hip in the sky chart. There is something quietly poetic about a galaxy named for someone in chains, who was eventually set free, for the galaxy itself, despite being bound to us by gravity, is not trapped so much as it is in motion. It has always been moving. In the mythology, it was Perseus who came to Andromeda, across the water. In the sky's long story, it is light that crosses the void. The names we give stars and galaxies carry more emotional truth than we sometimes notice. The most prominent of Andromeda's satellite galaxies is M32, also designated NGC 221, a compact elliptical galaxy that sits conspicuously close to Andromeda's southern edge in our sky. M32 is a dense, tightly packed world containing tens of millions of stars compressed into a relatively small volume, giving it one of the highest stellar densities of any galaxy known. It was first catalogued by Guillaume Le Gentil in 1749 and is clearly visible through a small telescope as a sharp, compact smudge beside its much larger host. What makes M32 particularly fascinating is the evidence suggesting it may once have been a much larger spiral galaxy, a peer, not a satellite. that was gradually stripped of its outer stars by Andromeda's gravity over billions of years, leaving behind only this dense, resilient core. What we see today may be a survivor, hollowed by proximity, still burning. The second major satellite of Andromeda is M110, designated NGC 205, a dwarf elliptical galaxy that balances on the northern side of Andromeda's disk, visible to the naked eye under exceptional conditions and easily seen through binoculars. Unlike M32, which is almost featureless in imagery, M110 shows traces of dust clouds within its core, an unusual feature for an elliptical galaxy which are typically gas and dust poor. This hints at a complexity in M110's history. Some relatively recent star formation, some disruption or infall of material, some internal process still quietly at work. Charles Messier himself noted M10-110 when he catalogued M31 in 1773, but did not include it in his official list. An oversight later corrected when historians confirmed his own observational notes described it clearly. Messier saw it, but did not know what to make of it. In that, he was not unlike the rest of us, standing before something vast. Beyond M32 and M110, Andromeda hosts a considerable extended family of dwarf satellite galaxies. Small, irregular, or spheroidal systems that orbit at greater distances from the main galactic disk. Astronomers have identified over 24 confirmed satellites, with names like Andromeda I1 through Andromeda Hux XI, a numbering system that sounds more like the naming of a dynasty than a catalogue, and perhaps that is fitting. Each of these dwarfs is a sparse collection of stars, loosely bound by gravity, containing relatively little gas and almost no ongoing star formation. They are old things. Most of their stars formed in the early universe, in the first billion years after the Big Bang, and have been burning slowly and dimly ever since. They are the quiet retainers of Andromeda's court, less brilliant than the central palace, but just as ancient, just as enduring. One of the most striking features of Andromeda's outer environment is the giant stellar stream, a vast arc of stars that extends hundreds of thousands of light years from the main galaxy, curving through the surrounding intergalactic space like a long, pale scar. This stream is thought to be the remnant of a dwarf galaxy that strayed too close to Andromeda long ago and was pulled apart by tidal forces. As the smaller galaxy orbited Andromeda, it was gradually stretched and shredded, its stars distributed along the orbital path like beads spilled from a broken necklace. Stars from the disrupted dwarf now form a coherent stream visible to deep sky surveys, a ghostly trail left by something that was once, in its own small way, a complete world. The giant stellar stream is a record of a death, written in starlight, still flowing through the dark. Andromeda's entire outer region is wrapped in an enormous, diffuse stellar halo, a sphere of ancient stars extending 1,000,000 light-years or more in every direction from the galactic center. This halo is not a disk. It has no defined plane. It is a roughly spherical cloud of old, low metallicity stars, scattered thinly across an almost unimaginable volume of space. Many of these stars are thought to be the stripped remnants of smaller galaxies that Andromeda absorbed over its long history. Stars torn from their original birthplaces and scattered into the outer darkness, still gravitationally bound to Andromeda, but drifting through a kind of stellar exile. The halo also contains globular clusters, dense, ancient balls of hundreds of thousands of stars, orbiting far from the galactic disk in long, slow paths that take hundreds of millions of years to complete. Andromeda possesses a remarkable population of globular clusters, dense, spherical assemblages of old stars that orbit the galaxy at various distances, from close to the central bulge to far out in the stellar halo. Current counts suggest Andromeda harbors somewhere between 450 and 500 confirmed globular clusters, which is significantly more than the roughly 150 associated with the Milky Way. Some of Andromeda's clusters are extraordinary. One designation in particular, Male 2, also known as G1, is the most intrinsically luminous globular cluster in the entire local group. It is so massive that some astronomers have proposed it may not be a true globular cluster at all, but rather the stripped nucleus of a dwarf galaxy that was long ago captured and swallowed. G1 may be, in other words, a survivor, the last heartbeat of something that was once more than a cluster, still orbiting, still shining. The stars within Andromeda are not all the same age, and this tells a rich story about the galaxy's history and evolution. Astronomers refer to the older stars, those born in the early universe, more than 10 billion years ago, as population 2 stars. They are typically dim red and composed almost entirely of hydrogen and helium, because heavier elements had not yet been forged in sufficient quantities during the early universe. Andromeda's central bulge and halo are rich in these ancient stars, giving the core that characteristic warm, amber glow. The spiral arms, by contrast, contain younger population I stars, richer in carbon, oxygen, iron, and other elements, produced by previous generations of stellar life and death. The diversity of stellar populations within a single galaxy is like reading a book in which every chapter was written in a different century, all bound together under one cover. In 2005, astronomers made an unexpected discovery in the outskirts of Andromeda. A smooth, thick disk of stars, extended disk of older, more diffuse stellar material. This extended disk was found to be tilted relative to the main stellar disk, suggesting it formed through a different process, possibly through the accretion of stars stripped from satellite galaxies over long periods of time. The existence of this component added a new layer of structural complexity to our understanding of Andromeda, and by extension to our models of how large spiral galaxies grow and evolve. It is a reminder that galaxies are not simple objects. They are layered, historical, accumulated systems, grown from mergers, accretions, and collisions stretched out over billions of years, with each event leaving a mark somewhere in the structure that a careful observer can still detect. The Triangulum Galaxy, known as M33 or NGC 598, is the third largest member of the local group and sits in a complex gravitational relationship with Andromeda. At roughly 3 million light-years from Earth, M33 is slightly more distant than Andromeda, and the two appear to be loosely interacting. Some models suggest that M33 may itself be a satellite of Andromeda, orbiting at a vast distance. M33 is a beautiful, loosely wound, face-on spiral, smaller than both the Milky Way and Andromeda, but actively forming new stars in its wide open arms. Under dark skies, it is also technically visible to the naked eye. The most distant naked eye object after Andromeda, at 3 million light-years, the trio of Andromeda, the Milky Way, and M33 forms the gravitational backbone of the local group. 3 interacting spirals slowly pulling on one another, across the deep dark of intergalactic space, the space between Andromeda and the Milky Way. Approximately 2.5 million light-years of it is not truly empty. It contains intergalactic gas, a very sparse scattering of stars, and the occasional isolated globular cluster or stellar stream drawn out from one of the two major galaxies long ago by the complex web of gravitational interactions between them. This region has no name in any human mythology. It is simply the in-between, the void that our light is crossing right now as it travels from one galactic family to another. In 4 billion years, when the collision between Andromeda and the Milky Way is well underway, this gap will no longer exist. The two spirals will overlap, their outer halos first, then their disks, then their central bulges, until the distinction between here and there loses its meaning and both galaxies begin the long, gentle process of becoming something new and singular. Andromeda's disk contains a series of prominent dust lanes, dark ribbons of cold molecular gas and complex carbon compounds that run through its spiral arms, silhouetted against the brighter stellar background behind them. These dust lanes are not merely visual features. They are the nurseries of future stars. Within the compressed, frigid interior of these molecular clouds, gas gradually collapses under its own gravity, fragmenting into clumps that grow dense and hot at their cores until nuclear fusion ignites and a new star is born. A process that takes millions of years and leaves behind a bright young stellar association expanding outward from its birthplace. The dust lanes of Andromeda are particularly visible when the galaxy is imaged in detail, sweeping dark curves against a background of older, reddish stars. They are where the future of that galaxy is being quietly and patiently constructed. Andromeda glows at multiple wavelengths beyond visible light, and what astronomers see when they observe it in infrared, ultraviolet or ordinary optical telescopes. In infrared light, the warm dust lanes in its spiral arms ignite in bright glowing arcs, tracing the regions of star formation and heated molecular material with high contrast. In ultraviolet, the hot, young blue stars along its arms burn intensely, making the star-forming rings of Andromeda dramatically apparent. In X-ray observations, point sources of high-energy emission reveal populations of neutron stars and black hole binary systems, ancient stellar remnants consuming material from companion stars and emitting powerful pulses of radiation in the process. Each wavelength reveals a different layer of the same galaxy, the way different types of light reveal different rooms in the same vast inhabited house. The supermassive black hole at the center of Andromeda, designated M31, in the notation astronomers use for central galactic black holes, has a mass estimated between 100 and 140 million times that of our Sun. It is one of the most massive black holes known in the local group, and its presence is inferred not by observing the black hole directly, but by watching the behavior of the stars closest to it. Stars near the galactic center move at extraordinary speeds, their velocity shaped by the gravity of the invisible mass at the core. The faster they move, the more mass must be present to account for that speed. By charting stellar velocities in Andromeda's nucleus with fine precision, astronomers have reconstructed the gravitational profile of the center and concluded that only a black hole of this magnitude could explain what the stars are doing. The black hole announces itself through motion. One of the most puzzling and persistently fascinating discoveries in Andromeda's core is its double nucleus. The observation, first clearly resolved by the Hubble Space Telescope in 1993, that the center of Andromeda does not have one bright peak of stellar density. but two. The two peaks are designated P1 and P2. P2 is the true center, the location of the supermassive black hole. P1 is offset from the black hole by several light years and appears brighter in visible wavelengths, which created the long-standing mystery of why the galactic center seems to have two hearts. For years, astronomers debated whether P1 was a second nucleus, the core of a previously swallowed galaxy, or something else entirely. The answer, when it came, was elegant and deeply satisfying, and it has to do with the way orbits behave when they are packed very close to a gravitational singularity. The explanation for Andromeda's double nucleus comes from a model proposed by astronomer Scott Tremaine in 1995, and it remains the accepted understanding today. P1 is not a second nucleus at all. It is an illusion produced by orbital dynamics. The stars closest to the black hole travel in elliptical orbit, and because stars slow down near the far point of an ellipse, just as a comet slows when it swings to the outer edge of its orbit, they spend more time on one side of the ellipse than the other. Over the long run, this means more stars are found on one side of the orbit at any given moment, creating a brightness asymmetry. What appears to be two distinct nuclei is actually the same population of stars moving in a single eccentric disk, bunching up on the far side because orbital mechanics demands it. The cosmos is full of illusions that, once explained, become more beautiful than the mystery was. At the very center of P2, the true nucleus, overlapping the position of the supermassive black hole, astronomers have identified a compact cluster of young, hot blue stars. This is extraordinary. Young stars should not be able to form so close to a supermassive black hole. The tidal forces in that region are so intense that they would normally tear apart any molecular cloud before it could collapse into stars. The presence of young blue stars at the nucleus of Andromeda is therefore a genuine puzzle, one that has led astronomers to propose that stars may have formed slightly further out and then migrated inward, or that some unusual mechanism allows star formation to occur in regions of extreme tidal stress. Either way, the blue stars burn there now, a small, fierce population of young stellar lights orbiting a mass 100 million times that of our Sun, intimate and improbable. Surrounding the very center of Andromeda, at a distance of a few hundred light-years from the black hole, sits a dense structure known as the nuclear star cluster. Nuclear star clusters are found at the centers of most large galaxies and are among the densest stellar environments in the known universe. Regions where the concentration of stars per cubic light-year is orders of magnitude higher than in ordinary galactic regions. Within Andromeda's nuclear cluster, stars orbit at speeds that would feel breathtaking to observe. Tens or hundreds of kilometers per second, their paths shaped almost entirely by the gravity of the central black hole. Despite this dynamism, the cluster appears visually compact and relatively smooth, its stars so numerous and so close together that no individual one can be resolved. Only the collective glow of millions packed into a bright, compact ellipse at the galaxy's core. Andromeda's core emits X-rays, a form of high-energy radiation invisible to human eyes but detectable by space-based observatories such as the Chandra X-ray Observatory and XMM Newton. The X-ray sources within Andromeda's central region include a population of X-ray binary systems, stellar remnant objects, black holes, or neutron stars. In tight orbits around ordinary companion stars, pulling material from their companions in a process called accretion. As the infalling gas compresses and heats to millions of degrees, it radiates in X-ray wavelengths. the central black hole M31 itself is a weak X-ray source, currently accreting very little material and therefore releasing far less energy than an active galactic nucleus would. Its quiet state makes it almost undetectable by comparison to quasars or Seyfert galaxies, which are powered by dramatically more active central black holes. Andromeda's core sleeps, but in its sleep it still glows. The center of Andromeda is dominated by stellar populations that are very old, stars born in the first few billion years of the universe's history, when Andromeda itself was still assembling from smaller fragments of gas and metal-poor material. These old stars have had billions of years to evolve, and many of the most massive among them long ago completed their lives, exploding as supernovae and seeding the surrounding medium with heavier elements. What remains in the bulge are the longer-lived, lower-mass stars, K and M-type orange and red stars, evolving slowly, burning at low temperatures, contributing to the warm amber glow that gives the central bulge its distinctive color. Giants and subgiants populate the upper reaches of the stellar age sequence, swollen and luminous, their surfaces cool and vast. They are the patriarchs and matriarchs of Andromeda's stellar family, the ones that have been there from nearly the beginning. The bulge of Andromeda, the central, roughly spherical region of densely packed older stars, extends several thousand light-years outward from the nucleus in all directions before transitioning into the more flattened stellar disk and its spiral arms. It glows with the combined light of billions of sun-like and subsolar stars, giving it a yellowish-white color in photographic imagery that contrasts beautifully with the blue-white spiral arms beyond. The bulge is thought to have formed very early in Andromeda's history, in a period of intense rapid star formation, sometimes called a starburst, a phase when gas was plentiful, gravity was aggressive, and stars formed in enormous quantities in a relatively short span of cosmic time. Since that early burst, the bulge has been mostly quiet. Its stars simply age, their light slowly reddening, their cores gradually cooling, the chapter of their formation long closed. Embedded within and around Andromeda's central region are numerous globular clusters, ancient, dense balls of hundreds of thousands of gravitationally bound stars, some of them among the oldest structures in the universe. The globular clusters near Andromeda's core are thought to have formed during or shortly after the formation of the main galaxy, over 10 billion years ago, and have survived to the present by remaining in stable orbits around the galactic center. They are extraordinarily long-lived objects, unlike most structures in astrophysics. Globular clusters do not easily dissolve. They hold together through mutual gravity for timescales that rival or exceed the current age of the universe. Within each one, hundreds of thousands of stars share a common birthplace, a common age, and a common chemical composition, a kind of cosmic community, orbiting together, aging together, orbiting together through the long dark of billions of years. One of the key tools astronomers use to study Andromeda's central structure is spectroscopy, the technique of spreading the light of an astronomical object into its constituent wavelengths and reading the resulting spectrum like a fingerprint. The precise pattern of absorption lines in the spectrum of Andromeda's core tells astronomers what elements are present, what the temperature of the stellar population is, how old those stars are on average, and how fast the stars are moving toward or away from us along the line of sight. Spectroscopic measurements of the core have revealed that the stars very close to the central black hole are moving at extraordinary high speeds, consistent with a very concentrated mass of the center. This technique, Reading light to understand mass, motion, temperature, and time is one of the great quiet marvels of observational astronomy, a way of listening to what stars are saying without ever being anywhere near them. The gravitational influence of Andromeda's central black hole extends outward for a sphere known as the sphere of influence, the region within which the black hole's gravity dominates over the distributed mass of the surrounding stars. For M31, this sphere of influence has a radius of several light-years. Beyond that boundary, the collective gravity of billions of stars gradually takes over, and the black hole becomes just one component of the overall gravitational landscape, rather than the single dominant force. Within the sphere of influence, however, stellar orbits are governed almost entirely by the black hole's pull. Stars there trace their paths around the singularity with a geometric precision that feels almost mechanical, almost elegant. It is the same physics that governs a planet orbiting a star, but applied at a scale of millions of solar masses and expressed in the motions of millions of stars. Andromeda's core has been carefully mapped not only in visual light, but across the electromagnetic spectrum: radio, infrared, optical, ultraviolet, X-ray. And each mapping reveals a slightly different and equally detailed portrait of the galactic center. Radio observations reveal jets and filaments of charged gas. Infrared imaging penetrates the obscuring dust lanes to show the warm stellar populations beneath them. Ultraviolet picks out the young blue stars in the nucleus. X-ray surveys count the populations of stellar remnants. Together, these layers of observation have built an extraordinary detailed three-dimensional model of Andromeda's core, a model that continues to be refined with each new instrument and each new observing campaign. The accumulated knowledge we have of this single small region, a few thousand light-years across, at a distance of 2.5 million light-years, is a testament to patient, cumulative scientific effort stretching across most of a human century. Despite all we know about it, the core of Andromeda still holds genuine mysteries. The precise mechanism by which the double nucleus formed, the origin of the young blue stars so close to the black hole, the detailed structure of the nuclear star cluster, all remain active areas of research and debate. Some of the questions we are asking about Andromeda's center now could not even have been formulated 50 years ago, because the instruments and the conceptual frameworks to ask them did not yet exist. Astronomy is a discipline of perpetual depth. Every answer reveals a deeper question. Every solved mystery opens a door to a room full of new ones. The center of Andromeda is, in this sense, an ideal object, close enough to study in genuine detail, far enough to still contain secrets, massive enough to be consequential, and old enough to carry within its light the record of things that happened before our solar system existed. Andromeda's spiral arms are not as cleanly defined as those of some other classic spiral galaxies, and astronomers have noted for decades that its arm structure is somewhat patchy and irregular when examined closely, a characteristic that may reflect its long history of gravitational interactions with its satellite galaxies, rather than 2 or 4 pristine, symmetric arms sweeping smoothly from the center. Andromeda's outer disk shows a network of overlapping and offset rings or arm segments, some of which appear to have been disturbed from their original positions. The most prominent feature is not a conventional spiral arm, but a large ring of star formation at roughly 32,000 light-years from the center, sometimes called the 10 kiloparsec ring which is one of the most active star-forming regions in the entire local group. This ring glows in infrared and ultraviolet light, betraying the warmth of newborn stellar regions embedded within it. The 10 kiloparsec ring, the dominant star-forming ring in Andromeda's disk, is thought by some astronomers to be the result of a head-on collision between Andromeda and its compact satellite M32 in the relatively recent astronomical past, perhaps 200 million years ago. According to this model, M32 passed through the center of Andromeda's disk like a stone dropped into still water, generating a ring-shaped density wave that propagated outward through the disk and triggered the collapse of gas clouds into new stars along its path. The ring structure we see today would then be the visible, lingering signature of that ancient impact, a ripple still moving through the stellar medium hundreds of millions of years later. Whether this model is correct remains an open question in galactic dynamics, but it is a compelling one, and it illustrates how the history of a galaxy is written into its present structure in ways that patient observation can decode. Within the star-forming regions of Andromeda's disk, the raw material for new stars is molecular hydrogen, the simplest and most abundant molecule in the universe. Cold molecular clouds, some spanning hundreds of light years, drift through the galactic disk, held together by self-gravity and shielded from destructive radiation by their own depth and density. When these clouds are compressed by a density wave, by the shock of a nearby supernova, by the gravitational nudge of a passing satellite, they begin to fragment. Smaller and smaller clumps form within the larger cloud, each growing denser, each pulling in surrounding gas, each heating at its core. Eventually, at the center of the densest fragment, temperatures surge high enough for hydrogen nuclei to begin fusing into helium. A protostar ignites. A sun is born. The whole sequence, from undisturbed cloud to burning star, takes millions of years, which is barely a breath by galactic standards. The most massive stars that form in Andromeda's disk live extraordinarily brief and dramatic lives. Stars with masses 20, 30, 50, or even 100 times that of our sun burn through their hydrogen fuel so rapidly that their lives last only a few million years. A vanishingly small duration compared to the 10 billion year lifespan of a star like our Sun. These massive hot blue stars, called O-type and B-type stars, radiate with a luminosity that can be tens or hundreds of thousands of times greater than our Sun. They ionize the gas around them, carving out glowing bubbles of hot, thin plasma called HII regions, the pink and red nebulae seen in deep astronomical photographs. When they exhaust their fuel, they die violently in supernova explosions, briefly outshining the entire rest of the galaxy before collapsing into neutron stars or black holes. They are brief, bright, necessary. Supernovae occurring within Andromeda are among the most energetic events in the local group, and astronomers watch for them with great interest, despite the difficulty of detecting them across 2.5 million light-years. A supernova in Andromeda would briefly flare to a magnitude visible to the naked eye, perhaps rivaling the planet Venus at its brightest, before fading over weeks and months. The last confirmed supernova candidate, observed near Andromeda, occurred in 1885. Designated S Andromedae, which briefly reached naked-eye visibility in the constellation and was observed by multiple astronomers at the time. At the time, Andromeda's true distance was not understood, and the supernova's brightness confused early estimates of the nebula's nature. In retrospect, the event was a Type Ia supernova, the thermonuclear detonation of a white dwarf, and its light, arriving at Earth after 2.5 million years of travel, gave 19th century astronomers one of their first puzzling clues about the true scale of what they were looking at. After massive stars explode as supernovae, they leave behind extraordinary compact remnants. The most common are neutron stars, city-sized objects containing the mass of approximately 1.4 suns, compressed into a sphere roughly 20 kilometers across. The density of a neutron star is almost beyond imagining. A teaspoon of its material would weigh billions of tons on Earth. Some neutron stars rotate with tremendous speed, emitting beams of radio waves that sweep past Earth, like a lighthouse beam. We call them pulsars. Others sit in binary systems, accreting material from a companion star and emitting bursts of X-rays. More massive stellar remnants collapse further still, past the neutron star stage, to form stellar mass black holes, points of infinite density enclosed within event horizons. Andromeda's disk is populated with hundreds of such objects, the compact and permanent remains of stars that lived fast and burned brilliant. Not all stars in Andromeda's disk end violently. Stars with masses similar to or lower than our Sun follow a gentler, longer path through their stellar lives. They spend the majority of their existence, billions of years, fusing hydrogen into helium in a stable, steady state. Then, as their hydrogen runs low, they expand into red giants, their outer envelope swelling to perhaps 100 times their original diameter, while their cores shrink and heat. Eventually, they expel those outer layers in a slow, elegant exhalation. A planetary nebula, a glowing shell of gas illuminated by the now exposed ultraviolet bright core. What remains at the center is a white dwarf, a dense, slowly cooling cinder of carbon and oxygen. No longer undergoing fusion, simply radiating its stored heat into space over trillions of years. The Milky Way is full of white dwarfs, so is Andromeda. They are the quiet majority of endings. Andromeda's spiral disk contains a thin layer and a thick layer. Astronomers refer to these as the thin disk and the thick disk, mirroring similar structural components identified in the Milky Way. The thin disk is where most of the gas, dust, and young stars are found. It is relatively flat and narrow, perhaps 1,000 light-years deep, and it is the home of ongoing star formation and the brilliant blue-white stars of recent birth. The thick disk is older, more diffuse, and more vertically extended. It contains an older population of stars with more chaotic orbital histories, stars that were likely scattered from their original thin disk orbits by gravitational disturbances over many billions of years. The presence of both a thin and thick disk in Andromeda gives astronomers a layered record of the galaxy's star formation history. The thick disk encoding the early turbulent chapters, the thin disk still writing the current ones. Among the most visually stunning features of Andromeda's spiral arms are the OB associations, loose groupings of the youngest, hottest, most massive stars, clustered together because they were born recently from the same parent molecular cloud. OB associations are not gravitationally bound in the way that globular clusters are. They are more like a diaspora. Born close together, they gradually drift apart over millions of years as their individual orbital paths through the galaxy diverge. Within each association, the most massive stars rush through their lives, ionizing surrounding gas, triggering compression waves in adjacent molecular clouds, and eventually exploding as supernovae. that both terminate their own brief lives and, paradoxically, trigger the birth of new stars in the shockwave compressed gas around them. The spiral arms of Andromeda are threaded with these associations, chains of bright, short-lived lights tracing the compression zones that run along the inner edges of the arm structure. The interstellar medium of Andromeda's disk, the material between the stars, is a complex, dynamic, multi-phase environment, not the empty void that the word space might suggest. It contains cold, dense, molecular clouds, where temperatures hover near absolute zero. It contains warm, diffuse atomic hydrogen at thousands of degrees. It contains hot, tenuous plasma at millions of degrees, heated by supernova shockwaves and stellar winds. These phases coexist in a perpetual turbulent cycle. Cold clouds collapse into stars. The darks, stars heat and ionize their surroundings. Massive stars explode and inject hot gas into the medium. The hot gas cools and condenses, eventually forming new cold clouds from which the next generation of stars can grow. The interstellar medium is not a backdrop to the story of the galaxy. It is an active participant in it, constantly recycling, constantly being processed, a perpetual medium of transformation in which nothing is permanently wasted. Star clusters in Andromeda's disk, open clusters of young stars loosely held together by mild mutual gravity, serve as age markers for the galactic disk's star formation history. By studying the color and brightness distributions of stars within these clusters, a technique called color magnetogram analysis, astronomers can determine with good precision how old each cluster is. Very blue, luminous clusters are young, perhaps only tens of millions of years old. Redder, dimmer clusters may be hundreds of millions of years old, their most massive members long since dead. By mapping the ages and locations of hundreds of such clusters across Andromeda's disk, astronomers can reconstruct the spatial and temporal pattern of star formation across the galaxy. Which regions were active long ago, which are active now, which have been quiet for billions of years. The disk is a palimpsest, and the clusters are its annotations. When astronomers observe Andromeda through radio telescopes tuned to the 21-centimeter wavelength, the characteristic emission of neutral atomic hydrogen, they see a map of the galaxy that is very different from the optical image. The neutral hydrogen, itch-eyed disk, extends much further than the visible stellar disk, stretching to greater radii, tracing the outermost edges of the galactic potential well where gas has pooled but star formation has not yet ignited. Warps in the hydrogen disk at the outer edges of Andromeda have long been attributed to the gravitational tidal forces of its satellite galaxies, M32, M100, 10, and other dwarfs, pulling gently on the outer disk and distorting it from a perfect plane into a gentle wave. These warps are common features of spiral galaxies and serve as a record of gravitational interaction, a reminder that no galaxy, not even one as large as Andromeda, is an island unto itself. Everything is in conversation with everything else. The dust lanes of Andromeda, those dark, sweeping ribbons of cold, molecular material visible even in modest telescopic photographs, are far more than visual features. They are, in a very real sense, the future. Within those clouds, at this very moment, molecular cores are contracting. Protostars are forming. Some number of them will not survive. They may be disrupted by radiation pressure from nearby massive stars before they can fully ignite. But others will persist long enough for fusion to begin, long enough to acquire a disk of gas and dust around them, long enough perhaps to accumulate rocky planets in the intermediate orbital zone, where temperatures allow liquid water. In some of Andromeda's dust lanes right now, something may be igniting for the first time, something that billions of years from now might become the birthplace of observers, looking back toward the Milky Way from 2.5 million light-years away, wondering what lives there. The collision between the Andromeda Galaxy and the Milky Way is not a prediction based on assumption. It is a conclusion drawn from extraordinary precise measurements of Andromeda's velocity relative to our galaxy, using the Hubble Space Telescope and, more recently, the Gaia Space Observatory. Astronomers have measured both the radial velocity of Andromeda, how fast it is moving directly toward us along our line of sight, and its transverse velocity, how fast it is moving sideways across the sky. Both components have now been pinned down with remarkable accuracy. The result is unambiguous. Andromeda is on a collision course with the Milky Way. It is approaching at roughly 110 kilometers per second toward us, with a relatively small sideways component, small enough that the two galaxies will not pass each other at a safe distance, but will instead meet, interpenetrate, and ultimately merge into a single system. The encounter is not a possibility, it is an appointment. The first close approach between Andromeda and the Milky Way is expected to occur in approximately 4.5 billion years from now. At that point, the two galaxies will not merge cleanly or immediately. Instead, they will pass through each other, a ghostly interpenetration of two vast stellar systems, their stars threading between each other without collision, their mutual gravity pulling and distorting each other's shapes dramatically. Computer simulations of this first encounter showed the two galaxies warping into extraordinary forms, long tidal tails of stars, thrown outward by gravitational forces, the spiral arms disrupted and curling around each other in a slow, raking state. The two galactic disks tilting and curling around each other in a slow, warping. Silent choreography of immense gravitational forces. After this first passage, both galaxies will continue beyond each other, slow turn under their mutual gravity, and fall back together for a second pass. And then a third. The merger is not a moment, it is a process. One of the most reassuring aspects of the coming galactic collision is that individual stars within each galaxy are extraordinarily unlikely to collide with one another. This is because, despite the trillion stars in Andromeda and the hundreds of billions in the Milky Way, the distances between individual stars are so enormous that the two clouds of smoke, the nearest star to our Sun, Proxima Centauri, is over 4 light-years away. Scaled to physical intuition, if our Sun were the size of a tennis ball, Proxima Centauri would be another tennis ball located roughly 2,000 kilometers away. The space between stars is not merely large, it is overwhelming. When the galaxies merge, the stars will drift and reorganize under new gravitational influences, but the probability of any two individual stars making physical contact is vanishingly, almost absurdly small. While the stars themselves will not collide, the gas clouds between them very much will. Unlike stars, the interstellar gas in both galaxies occupies large volumes and will interact directly when the two disks begin to interpenetrate. Gas clouds from the Milky Way and Andromeda will slam into each other at high relative velocities, compressing and heating and shock waves that propagate through the interstellar medium. These compressions will trigger enormous bursts of star formation. episodes in which gas collapses rapidly into new stars at rates far exceeding what is happening in either galaxy today. The merging system will likely experience what astronomers call a starburst, a period of dramatically heightened stellar birth driven by the collisional compression of gas clouds. Brilliant new clusters of young blue stars will ignite across the merged system, illuminating it with a ferocious, brief luminosity before dimming as the gas is gradually consumed or expelled. The two supermassive black holes at the centers of the Milky Way and Andromeda will also eventually find each other. As the two galaxies merge, the black holes will sink toward the center of the growing combined system through a process called dynamical friction, a gravitational braking effect in which the dense stellar environment around each black hole gradually robs it of orbital energy, causing it to spiral inward toward the center of mass. Over hundreds of millions of years, the two black holes will draw closer and closer together, forming a binary black hole system, two enormous singularities orbiting each other at increasingly close range. Eventually, they will spiral together and merge in a cataclysmic event that radiates an extraordinary burst of gravitational waves, ripples in space-time propagating outward at the speed of light. The merged black hole will be the largest in the resulting galaxy, inheriting the combined mass of both predecessors. Gravitational wave observatories of the future, perhaps instruments far more sensitive than the current LIGO and Virgo detectors, may be capable of detectors the forms in the early stages of the Andromeda Milky Way merger. The signal from two supermassive black holes spiraling together, each containing tens or hundreds of millions of solar masses, would be among the most powerful gravitational wave events ever generated in the local group. The frequency of these waves would likely fall in the low frequency range detectable by space-based observatories. Instruments like the planned LISA mission, a triangular array of spacecraft sensitive to gravitational oscillations, far too slow for ground-based detectors. In a genuinely profound sense, the merger of our two galaxies will not be silent. It will produce a sound, not in air, but in space-time itself, audible in principle to instruments sophisticated enough to listen for it. What happens to our solar system during the merger? The honest answer is probably very little. In physical terms, our Sun and its planets orbit the center of the Milky Way at roughly 26,000 light-years, well within the disk, but far from the central regions where the most dramatic gravitational interactions will occur. During the first passage of the two galaxies through each other, the Sun may be thrown into a somewhat different orbit, perhaps pushed to a larger distance from the galactic center, or deflected to a higher inclination orbit. But the probability of the solar system being disrupted or ejected from the galaxy entirely is relatively low. Earth, if it still exists, given the Sun's own red giant phase will begin around the same time, would remain orbiting its star. The sky from that Earth, however, would look very different. A dynamic, irregular blaze of stars and galactic structure, entirely unlike the quiet band of the Milky Way we see tonight. Computer simulations of the Andromeda Milky Way merger, run by teams including those at the Space Telescope Science Institute using high-resolution N-body and hydrodynamical codes, show a remarkably consistent sequence of events across many model runs. First encounter, second pass, third encounter. Then, over a period of roughly 2 billion years following the initial contact, the two galaxy cores approach, spiral together, and coalesce into a single central structure. The extended stellar streams and tidal tails thrown off during the interaction gradually fall back into the growing merged system over subsequent billions of years. What emerges from the simulations is not a spiral galaxy. It is a large, smoothly glowing elliptical galaxy. A system in which the ordered rotation of the original disks has been replaced by a more randomized distribution of stellar orbits in all directions. The spirals are gone. Something new and quieter has taken their place. The resulting galaxy from the merger, nicknamed Milkomeda, or sometimes Milkomeda in informal astronomical parlance, will be a giant elliptical galaxy thought to resemble the large red ellipticals that dominate the cores of galaxy clusters throughout the observable universe. Giant ellipticals are among the most massive, oldest-looking galaxies known. They appear as smooth, featureless spheroids of amber-hued starlight, their gas mostly consumed or expelled, their star formation largely ended, their stellar populations old and cool. Milkomeda will not be particularly special by cosmic standards. It will be an average-sized elliptical for a field environment, somewhat larger than either parent galaxy, but not remotely among the giants of the universe. But it will contain within its stars all the history of both our galaxy and Andromeda. Every star that ever formed in either system, layered together into a new whole. The night sky, as seen from a planet in the merged Milky Galaxy, billions of years from now, will be extraordinary, where we now see the Milky Way as a pale band arching across the sky. An observer deep within Milkomeda would see stars in all directions, densely packed across the full celestial sphere, with no preferred plane, the signature of an elliptical galaxy's randomized stellar orbits. The triangulum galaxy, M33, will also likely have been drawn into the merger over this same time scale, having been gravitationally entangled with both the Milky Way and Andromeda throughout the process. The local group, on this timescale, may effectively reduce to a single dominant galaxy, Milkomeda, surrounded by a scattering of smaller dwarf systems. The distinction between our galaxy and their galaxy will have become meaningless, dissolved by gravity and time into a single unified, slowly cooling family of stars. Intriguingly, despite the merger, the universe's accelerating expansion, driven by the mysterious entity known as dark energy, means that the broader cosmic environment around Milkomeda will be growing ever lonelier over the same timescale. Galaxy groups and clusters beyond the local group are already receding from us faster than their gravity can keep pace with, and on timescales of tens of billions of years, the observable universe will shrink dramatically as distant galaxies are carried beyond our cosmic horizon by expansion. The local group, our gravitationally bound family, will remain together, holding its own against the dark energy tide. But the broader universe will become a darker, more isolated place. By the time Milkomeda is fully assembled, perhaps only the members of the local group will still be visible in the sky, the rest of the universe's trillions of galaxies having receded into an unreachable, lightless distance. There is something unexpectedly beautiful about the collision between Andromeda and the Milky Way, when viewed from the right emotional angle. Two galaxies, each the home of hundreds of billions of stars, each the product of billions of years of independent evolution, slowly drawn together by nothing more complicated than the basic physics of gravity, until they can no longer be told apart. No catastrophe, no destruction. Just a slow merging, a blending of histories, a new configuration of light emerging from the meeting of two old ones, the stars of Andromeda, that will one day be folded into the same galaxy as our Sun, have already been shining for billions of years. Some of them are older than our Sun. Some completed their lives and died before the Earth existed. In 4 billion years, their descendants and ours will share the same sky, the same galaxy, the same gravitational home, as if they had always belonged together. The evidence for dark matter in galaxies like Andromeda comes most directly from rotation curves. Measurements of how fast stars and gas at different distances from the galactic center are orbiting the galaxy. According to Newtonian gravity, stars at the outer edges of a galaxy, far from the main concentration of visible mass near the center, should orbit more slowly, just as the outer planets of our solar system orbit the Sun more slowly than the inner ones. But when astronomers actually measure the orbital velocities of stars and gas clouds in Andromeda and galaxies like it, they find something unexpected. The rotational speed does not fall off with distance. It stays roughly flat or even rises slightly, all the way to the outermost measurable reaches of the galactic disk. Something is providing an additional gravitational pull beyond what the visible stars and gas can account for. That something has been named dark matter. The dark matter associated with Andromeda is not distributed in a disk the way the visible stars and gas are. Instead, it occupies a roughly spherical halo, an enormous invisible envelope surrounding the entire galaxy in all directions, extending far beyond the edge of the stellar disk into the intergalactic medium. This halo likely has a radius of several 100,000 light years, or possibly over 1 million light years, dwarfing the visible galaxy it encloses. The halo is not uniform. It is thought to be clumpier in its inner regions and more diffuse at its outer edges, with a density that falls off gradually with distance from the center. Within this invisible sphere, the visible galaxy, its stars, its dust, its satellite galaxies, occupies only the innermost brightest and most densely lit fraction. The galaxy we see in photographs is, in a very real sense, just the illuminated core of something far larger and far less understood. What dark matter actually is remains one of the most important open questions in all of physics and cosmology. It is not ordinary matter, not atoms, not protons, not neutrons, not anything composed of the particles in the standard model of particle physics that physicists have confidently catalogued over the past century. It interacts gravitationally, as proven by its effects on galaxies, galaxy clusters, and the large-scale structure of the universe. But it does not interact electromagnetically, meaning it produces no light, reflects no light, and absorbs no light. Various candidate particles have been proposed: WIMPs, weakly interacting massive particles, axions, sterile neutrinos, primordial black holes. Each candidate has been searched for with extraordinarily sensitive detectors, and none has been definitively detected. Dark matter remains real in its effects, consistent in its gravitational behavior, and completely mysterious in its underlying nature. It is the universe's most carefully documented unknown, long before the term dark matter was formalized. The Swiss-American astronomer Fritz Zwicky observed in 1933 that the galaxies within the Coma cluster were moving too fast, far faster than the visible mass of the cluster could gravitationally sustain. By his rough calculation, the cluster should have flown apart long ago. Something unseen was providing the extra gravity to hold it together. Zwicky called this unseen material Dunkel Materie, dark matter. His observation was largely ignored for decades, considered an anomaly rather than a paradigm-shifting discovery. was not until the 1970s that astronomer Vera Rubin, studying the rotation curves of spiral galaxies, including Andromeda, arrived at the same conclusion through an entirely different observational route. Her meticulous measurements of stellar velocities across Andromeda's disk provided some of the most compelling early evidence that dark matter was not a curiosity in distant clusters, but a universal ingredient present in every galaxy, including the one now visible above us on clear night. Vera Rubin's work on Andromeda deserves particular attention in any meditation on this galaxy. Beginning in the 1960s and continuing through the 1970s, in collaboration with astronomer W. Kent Ford, Rubin measured the Doppler shifts in the spectra of stars and gas clouds at various distances from Andromeda's center, using the fact that objects moving toward us have their light shifted slightly toward the blue end of the spectrum, while objects moving away show a slight redshift. By comparing the shifts on opposite sides of Andromeda's disk, she could calculate rotational velocities at each radius. The flat rotation curve she found did not align with what the visible mass of the galaxy predicted. She published her results carefully, acknowledging the tension with existing theory while letting the data speak for itself. Her work on Andromeda and dozens of other galaxies became the most direct and reproducible observational evidence for dark matter in galactic scale systems. A legacy that reshaped modern astrophysics. Dark matter plays a foundational role in the formation of galaxies, not merely in their present-day dynamics. In the early universe, the distribution of dark matter was not perfectly uniform. There were tiny density fluctuations, regions where dark matter was slightly more concentrated than average. Imprinted by quantum processes in the first moments after the Big Bang, these slightly overdense regions had slightly more gravity than their surroundings. Over hundreds of millions of years, they drew in more dark matter, becoming denser still, while their surroundings became correspondingly emptier. The dark matter collapsed first into structures called halos, and it was within these halos that ordinary matter, gas, subsequently fell and cooled and fragmented into stars. Andromeda formed inside a dark matter halo. So did the Milky Way. Every galaxy in the observable universe grew from a seed of dark matter density long before a single visible star ignited to mark the spot. The boundary between Andromeda's dark matter halo and the Milky Way's dark matter halo is not sharp, and the two halos may already be overlapping, or nearly so, across the 2.5 million light-year gap between their visible centers. This overlap, if it exists, would mean that in a gravitational sense, our two galaxies are not fully separate systems. They are already entangled. Their dark matter halos may already be in the earliest stages of interacting, tugging gently on each other across the intergalactic void. The invisible architecture of each galaxy beginning to sense the pull of the other long before the first visible stars of one galaxy's disk have come close enough to the other to be seen with the naked eye. The merger may, in the most technical sense of gravitational influence, have already begun, not in the disk, not in the stars, but in the dark. One of the most powerful tools for studying the dark matter distribution around Andromeda and other galaxies is gravitational lensing. The phenomenon predicted by Einstein's general theory of relativity, in which mass curves the path of light passing near it. A concentration of dark matter, even though it produces no light of its own, will bend and distort the images of background galaxies seen through it, magnifying some, stretching others into arcs, occasionally producing multiple images of the same source. By carefully mapping these distortions in the images of galaxies behind Andromeda and the local group, astronomers can reconstruct the distribution of total mass, visible and dark, along the line of sight. The technique effectively uses the universe's own geometry as a measuring instrument. It requires no assumptions about the nature of dark matter, only that mass, in whatever form, bends light. And it does. It always does. Simulations of the universe's large-scale structure, from early projects like the Millennium Simulation to more recent efforts, like the illustrious 10 project, show that dark matter forms a cosmic web, a vast filamentary network of sheets and filaments and nodes that stretches across the observable universe, with galaxy clusters forming at the nodes where filaments intersect, like drops of water condensed at the junctions of a spider's web. The Milky Way and Andromeda, along with the rest of the local group, sit within one of these cosmic structures, a relatively quiet, modestly sized region between larger filaments, not at a massive node, but connected nonetheless to the broader web of cosmic matter. The dark matter filament in which we are embedded stretches toward the Virgo cluster, the nearest major galaxy cluster, exerting a gentle gravitational pull known as the Virgo-centric flow that slightly modifies the local velocity field of galaxies in our neighborhood. If dark matter has remained mysterious in terms of its particle identity, it has been extraordinarily well characterized in terms of its gravitational behavior. The profile of how dark matter density varies with radius in a typical galactic halo follows a well-established mathematical curve called the NFW profile, after cosmologists Julio Navarro, Carlos Frenk, and Simon White, who derived it from numerical simulations in the 1990s. This profile predicts a steep central density cusp at the galactic nucleus, and a more gradual decline outward. Real observational data from systems like Andromeda broadly support this shape, though some tension remains between simulation predictions and observations, particularly in the innermost regions of lower mass galaxies. These discrepancies are active areas of research, and their resolution may eventually tell us something profound about the nature of dark matter itself, whether it is truly cold and collisionless as assumed, or whether it has subtle self-interaction properties we have not yet quantified. The total dark matter content of Andromeda and its halo dwarfs the visible matter by an enormous margin. Current estimates suggest that dark matter accounts for roughly 85 to 90% of the total mass of a galaxy like Andromeda, with ordinary matter, stars, gas, dust, stellar remnants, making up only the remaining 10 to 15%. This means that everything we have described in previous chapters, the trillion stars, the satellite galaxies, the spiral arms, the star-forming rings, the ancient globular clusters, the supermassive black hole, all of that luminous structure constitutes only a small minority of what Andromeda actually is by mass. The galaxy we see is a kind of luminous foam on the surface of a far deeper, darker, and vaster structure. We have been admiring the smallest part of something much larger. The universe's primary ingredient is something we have never touched, never seen, and never fully explained. There is a strange comfort, perhaps, in the fact that dark matter is not merely an Andromeda problem. It is a universe problem. Every galaxy, every cluster, every filament of the cosmic web is dominated by it. We are embedded in it right now, wherever we are. The dark matter halo of the Milky Way extends to an uncertain but enormous distance in every direction from the galactic center, and we moved through it tonight, and we will move through it tomorrow, and it will not deviate us from our course by a measurable degree, and we will not feel it or detect it directly. It is simply present as it has always been, holding everything together in a gravitational silence that preceded the first star and will outlast the last. The universe is mostly dark, and that darkness, once accepted, is strangely restful, a reminder that the largest truths are often the quietest ones, operating beneath everything visible, shaping the world without announcing themselves. The earliest surviving written record of Andromeda as a distinct astronomical feature comes from the Persian astronomer Abd al-Rahman al-Sufi, who documented what he called a small cloud in his Book of Fixed Stars, completed around 964 CE. Al-Sufi was one of the great observational astronomers of the medieval Islamic world, meticulous, systematic, and deeply influenced by the Greek tradition while also correcting and expanding upon it. His descriptions of star positions and brightness were so careful that many remain accurate to this day by the standards of naked eye observation. The small cloud he noted near the star New Andromedae was Andromeda's Galaxy, the first documented observation of an object outside our own galaxy, though al-Sufi had no way of knowing that. He noted it simply because it was there, and because careful observers note things that are there. In that, he exemplified a timeless scientific virtue. For the centuries between al-Sufi's catalogue and the invention of the telescope, Andromeda's galaxy remained a curiosity in astronomical records, noted, catalogued alongside comets and nebulae, but not understood. Simon Marius, a German astronomer, observed it telescopically in 1612 and described it as resembling the light of a candle shining through horn, a beautiful pre-industrial simile for the diffuse, slightly luminous quality of distant light, diffused through translucent material. His description remains one of the most poetic early accounts of the object through optical instrumentation. For the next 3 centuries, the nature of Andromeda's nebula, whether it was a local cloud of gas or something far more distant, remained genuinely unresolved. Telescopes grew larger and more powerful. Photographs replaced the human eye at the focal point, but the fundamental question of what the spiral nebulae were did not have a definitive answer until the 20th century. The early 20th century saw one of the great intellectual debates in the history of astronomy, the so-called Great Debate of 1920, held at the Smithsonian Institution in Washington, D.C. In which astronomers Harlow Shapley and Heber Curtis argued opposing positions on the nature of the spiral nebulae. Shapley maintained that the spiral nebulae were relatively small, local objects, gaseous structures within or just beyond our own galaxy, which he believed to be the entirety of the stellar universe. Curtis argued the opposite, that the spiral nebulae were island universes, vast, distant systems of stars, comparable to the Milky Way itself, lying far outside our galaxy's boundaries. The debate was not cleanly resolved that evening. Both men had compelling evidence and compelling errors. The definitive answer came 3 years later, when Edwin Hubble's observations of Cepheid variables in Andromeda proved Curtis right and transformed cosmology forever. The 100-inch Hooker telescope at Mount Wilson Observatory in California, the instrument through which Hubble made his historic observations of Andromeda, was at the time of its completion in 1917 the largest telescope in the world, perched at an altitude of nearly 1,700 meters in the mountains above Los Angeles. It gathered light with a mirror nearly 2.5 meters across, enough aperture to resolve individual stars within the spiral structure of Andromeda for the first time under careful conditions. The nights at Mount Wilson in the 1920s were dark. Los Angeles had not yet sprawled its light pollution across the basin below. Hubble worked those nights methodically, photographing the same fields repeatedly, examining his plates under magnification, marking variable stars, building the observational case that would eventually overturn the prevailing cosmology. The work was quiet, slow, and precise. The discovery it produced was seismic. Hubble's 1923 discovery was recorded in a way that has since become one of the most famous annotations in the history of astronomy. On a photographic plate labeled H35, H, he had initially marked 3 objects he believed to be novae, brief stellar brightening events. Examining the plate again more carefully, he recognized that one of the 3 was not a nova at all, but a Cepheid variable, a pulsating star with a recognizable light curve. He crossed out the N he had written for nova and wrote above it, in his clear hand, the letters Bayar. That exclamation mark on a glass photographic plate in an observatory that still stands on a mountain in California marks the moment when the known universe doubled and then doubled again and continued to expand, in our awareness, if not in physical size, into the incomprehensibly vast structure we now call the observable universe. One annotated plate. One exclamation mark. Everything changed. Following Hubble's initial distance measurement, subsequent refinements improved the accuracy of Andromeda's estimated distance over the course of the 20th century. Early estimates placed Andromeda estimate. A crucial correction came in the 1950s when astronomer Walter Baade, working with the 200-inch Hale telescope at Palomar Observatory, discovered that there were 2 distinct types of Cepheid variable stars with different period luminosity relationships, a finding that had been conflated in earlier analysis and led to a systematic underestimate of extragalactic distances. When Baade applied the corrected calibration, the distance to Andromeda roughly doubled. Further refinements using modern instrumentation have since settled the value near 2.537 million light-years. Each revision was not a failure of earlier science, but an expression of how science actually works. Conclusions held provisionally, updated honestly when better data arrives, the model perpetually improving. The launch of the Hubble Space Telescope in 1990 transformed our ability to study Andromeda at a level of detail previously impossible from the ground. By operating above Earth's atmosphere, which blurs and distorts optical observations, the Hubble Space Telescope could resolve individual stars within Andromeda with extraordinary precision, performing photometry on millions of individual stellar sources at 2.5 million light-years. The pandramatic Hubble Andromeda Treasury Patriot Survey, completed in 2012, catalogued over 117 million individual stars in Andromeda across multiple wavelengths, the largest color magnetite diagram ever assembled for any galaxy. This data set enabled unprecedented studies of stellar populations, star formation history, dust distribution, and the structural properties of the galactic disk. It turned Andromeda from a nearby galaxy into a resolved stellar population, a laboratory for galactic physics that could not be replicated anywhere else at this level of detail. The Gaia Space Observatory, launched by the European Space Agency in 2013, has contributed to our understanding of Andromeda in a different but equally important way. Gaia's primary mission is to measure the positions, distances, and proper motions of over 1 billion stars within and around the Milky Way with extraordinary precision. Its accurate measurements of the Milky Way's own stellar population have allowed astronomers to better characterize the local group's dynamics, including refined constraints on the proper motion of Andromeda relative to our galaxy. These refined measurements are what allowed astronomers to confirm, with high confidence, that the collision between Andromeda and the Milky Way is essentially inevitable, and to narrow the uncertainty on when the first close approach will occur. By understanding our own galaxy more precisely, we understand what Andromeda is falling into, and the collision timeline has become steadily more constrained with each new data release. The James Webb Space Telescope, launched on Christmas Day 2021 and fully operational from 2022, observes primarily in infrared wavelengths, allowing it to see through dust that obscures optical observations and to detect the heat signatures of cool objects that emit little visible light. Applied to Andromeda, Webb has the potential to reveal star-forming regions in unprecedented detail, to characterize the stellar populations within dust-shrouded areas of the galactic disk, and to study the properties of its satellite galaxies and stellar streams with far greater sensitivity than any previous instrument. Webb's extraordinary angular resolution and sensitivity open entirely new parameter spaces for studying the nearest large galaxy. Questions that could not even be cleanly formulated before its launch may now be answerable. The telescope is, in a sense, a new chapter in the long conversation between humanity and Andromeda. A chapter whose first sentences are only now being written. Andromeda sits within the local group, which in turn sits within a much larger structure, the Virgo supercluster, a vast gravitationally associated conglomeration of galaxy groups and clusters centered on the Virgo cluster, about 65 million light-years away. The Virgo cluster at its center contains over 1,000 galaxies and enough mass to exert a measurable gravitational pull on the surrounding region, a pull known as the Virgocentric flow, which slightly retards the expansion of space in our local neighborhood relative to the broader Hubble flow. The local group, including both Andromeda and the Milky Way, is not itself falling into the Virgo cluster. It is moving too fast in a different direction to be captured, but it is gravitationally influenced by it. The supercluster is barely bound, if bound at all, and its ultimate fate in a universe dominated by dark energy is likely to be dispersal rather than collapse. In 2014, astronomers redrew the map of our local cosmic environment, with a landmark paper defining an even larger supercluster, of which the Virgo supercluster is merely one lobe. This structure, named Laniakea, meaning immeasurable heaven in Hawaiian, was identified by mapping the peculiar velocities of thousands of galaxies in the local universe and tracing them back to a common gravitational basin of attraction. Laniakea encompasses roughly 100,000 galaxies within a volume approximately 500 million light-years across, with a total mass of about 100 million billion solar masses. The Milky Way, Andromeda, and the entire local group sit near the outer edge of Laniakea, in a quiet, relatively underdense region far from its core. We are in the suburbs of a continent-sized cosmic structure, and the name given to that structure, immeasurable heaven, feels, in this context, genuinely earned. At the heart of Laniakea lies a gravitational focal point called the Great Attractor, a region of concentrated mass toward which thousands of galaxies, including our own local group, are flowing at detectable speeds. The Great Attractor sits at a distance of roughly 150 to 250 million light-years in the direction of the constellation Centaurus, and its mass is estimated in the tens of thousands of times that of our own galaxy. Andromeda, as part of the local group, participates in this flow, streaming along with the Milky Way and M33 and all the dwarf galaxies of our neighborhood in the general direction of this vast overdensity. Whether the name attractor is precisely accurate is debated. The structure may itself be part of a still larger flow toward the even more massive Shapley supercluster. The universe on its largest scales is never simply in one place. Everything is always already on its way somewhere else. Andromeda, embedded in the local group, embedded in Laniakea, embedded in the observable universe, a sphere roughly 93 billion light-years in diameter, containing an estimated 2 trillion galaxies, is in cosmic terms a perfectly average object in a perfectly average location. There is no center of the universe. There is no privileged position. Every observer in every galaxy sees the same Hubble flow retreating around them, the same cosmic web threading through the darkness, the same ancient light from the Big Bang glowing in microwave wavelengths from every direction in the sky. Andromeda is not special because it is the most extreme or the most dramatic galaxy in the universe. It is special because it is nearby, and it is knowable, and it reflects back to us in its stars and its structure and its long trajectory toward our own galaxy. Something about the universality of the processes that made it. It is not unique. It is typical. And in being typical, it tells us everything. Every photon of light arriving from Andromeda tonight has been traveling for 2.537 million years. It left its source, a star, a glowing nebula, a stellar nursery, before the genus Homo existed on Earth. It crossed the local void, threaded through the thin intergalactic medium, passed through the outer stellar halo of our own galaxy, moved through the thin disk of the Milky Way, and finally entered your atmosphere, struck your retina or a detector, and registered that signal is not a copy of the source. It is the actual light, the original photons, the original energy, unchanged in their fundamental nature by the crossing of millions of light years. When you look at Andromeda, you are not seeing a representation of it. You are receiving something it genuinely sent, at a moment in deep time, addressed to nothing in particular, caught by you entirely by accident. There is something profoundly intimate about that. The light from the stars of Andromeda that you might see on a dark night carries within it information about conditions in that galaxy 2.5 million years ago. We have no knowledge of what Andromeda looks like right now. Not in the sense of this moment, because that concept breaks down at cosmological distances. There is no universal now in a universe governed by relativity. What we call now is local, a property of our own reference frame, diffusing outward with the light we emit and dissolving into meaninglessness at very large distances. The Andromeda we see is the Andromeda of 2.5 million years ago. It has continued to evolve since then. Stars have been born and died. Satellite galaxies have moved in their orbits. The black hole has continued its silence. What it looks like at this moment, by any reasonable definition of this moment, is something we simply cannot know. We look back, always back. Among the stars of Andromeda, there are almost certainly planetary systems. This is not speculation. It follows logically from what we know about star formation and planet formation as universal processes. The mechanisms that produced our own solar system are not unique to the Milky Way. They are the natural consequence of angular momentum conservation in a collapsing molecular cloud, and they operate wherever molecular clouds collapse into stars, which is to say, everywhere. Surveys within our own galaxy have now confirmed that planets are extraordinarily common. Most stars host at least one, and planetary systems with multiple worlds appear to be the norm rather than the exception. Among Andromeda's trillion stars, by simple extrapolation, there may be hundreds of billions of planets, some of them orbiting at the right distance from the right kind of star, will have liquid water. Some of them perhaps have more than that. We don't know. We may never know. But the arithmetic is hard to argue with. One of the quieter implications of Andromeda's existence is what it suggests about the nature of the universe as a habitat. If planets are common in our galaxy and common in Andromeda, and both galaxies are typical members of a universe containing 2 trillion galaxies, then the total number of planets in the observable universe runs to numbers that exceed the descriptive power of ordinary language. The number of potentially habitable planets, those in the so-called Goldilocks zones of their stars, is estimated by various approaches to be in the tens of billions in the Milky Way alone. Across the observable universe, the number of worlds where conditions might permit liquid water is, by conservative estimates, larger than the total number of grains of sand on all the beaches of Earth. We are not asked by this arithmetic to conclude that the universe is teeming with life. We are only asked to sit with the scale of the possibility. That is enough for tonight. Andromeda is receding from us in one important sense, even as it approaches in another. The overall expansion of the universe, which is not the motion of galaxies through space, but the expansion of space itself, carries distant for objects close enough to be gravitationally bound to us, like Andromeda. This expansion is overwhelmed by the mutual gravitational attraction between the 2 galaxies. But for objects beyond the local group, the expansion wins, and those galaxies are carried away from us continuously. In a universe trillions of years old, long after the collision of Andromeda and the Milky Way and the formation of Milkomeda, the observable universe will be smaller and darker. The galaxies that are now visible on the edge of our cosmic horizon will have been carried permanently beyond it by then. Future observers in Milkomeda will see a lonelier sky. Andromeda and the Milky Way, merged into one, will be the light that remains. There is a particular quality of ancient starlight that no description quite captures, the fact that many of the individual stars we observe in Andromeda no longer exist. Stars in Andromeda, as in any galaxy, have finite lifespans. The most massive ones burn out in millions of years. Some of the stars whose light is currently crossing the 2.5-million light-year gap toward us have already completed their lives and explosively, as supernovae perhaps quietly contracting into white dwarfs. The photons now arriving from those stars predate their death. We are seeing the light of things that are gone, not symbolically gone, literally gone. The source of the light no longer exists, but the light, once emitted, cannot be called back. It keeps traveling. It will keep traveling past us, outward into the intergalactic medium, until it is too redshifted to be detectable. The stars die. The light continues. There is something in that worth resting with Ristin. The act of looking at Andromeda connects you through the physics of light to a moment in time before your species existed. But it also connects you to every other human being who has ever looked at it. Al-Sufi in the 10th century, noting a small cloud in his careful star charts. Simon Marius, through the cold glass of an early telescope, reaching for a simile. Edwin Hubble at Mount Wilson, bent over a photographic plate in the small hours. Vera Rubin, running spectra through the night, watching the velocities tell a story the mainstream had not yet accepted. Every amateur astronomer who has ever pointed binoculars at the Andromeda region on an autumn evening and paused surprised to find it. Every child who has been shown the sky by someone who loved them and learned for the first time that the faint smudge above the square of Pegasus is not a cloud, not a star, but an entire second universe of suns. You are in that chain. You always were. The Andromeda Galaxy contains, by current estimates, something in the region of 5 to 10 billion years of remaining active star formation, time during which molecular clouds will continue collapsing, protostars will continue assembling, planetary systems will continue assembling, and whatever processes gave rise to self-aware beings on this small, rocky planet will have ample opportunity to repeat themselves an unknowable number of times. Our Sun has roughly 5 billion years remaining on the main sequence. The universe itself is estimated to be approximately 13.8 billion years old. The future of Andromeda, measured in remaining years of stellar activity, is comparable to the entire past history of the cosmos as we understand it. The story of Andromeda is not even half told. We are observing it at its midpoint, roughly a working middle-aged spiral galaxy in the prime of its productive life, doing what galaxies do without drama, without urgency, without any awareness of being observed. The name of the constellation Andromeda, and by extension, the galaxy, derives from a story about being chained and being rescued. But the galaxy named for that princess has never been trapped. It has always been in motion, moving through the local group, approaching the Milky Way, carrying its satellite galaxies in orbit around it, sweeping through the intergalactic medium in its long infall toward the gravitational center of the local group. Motion is the galaxy's most fundamental state. Every star within it is orbiting the galactic center. Every satellite galaxy is orbiting the main disk. The disk itself is rotating, turning once every few 100 million years. The galaxy as a whole is traveling through space. Even the supermassive black hole at its center is moving, carried along by the overall motion of the galaxy it anchors. Nothing in Andromeda has ever been still, not for a single moment in its 10 billion year history. The name is a beautiful irony, a galaxy always in motion, named for someone who was held in place. The light pollution that prevents most people living in cities from seeing Andromeda is one of the quieter losses of modern civilization. A severing, however practical in its cause, from a direct sensory link with something that human beings have been noticing above them for as long as human beings have been looking up. The galaxy has been there throughout all of recorded history. It was there when the first written languages were being invented, when the pyramids were being built, when the printing press was created, when the first radio signals drifted into the atmosphere, when the first rockets breached the edge of space. It has been visible above every civilization that has ever existed on this planet, in every era, patient and unchanging on human timescales. Finding a place dark enough to see it, a field, a hillside, a desert, and lying on your back and locating the faint oval glow in the constellation's hip is one of the most direct experiences of deep time available to a human being without any instrument at all. In the deepest sense, Andromeda is a mirror. Not in appearance, it does not look like our galaxy from any perspective we can access, but in nature. It is, as far as we can determine, the kind of galaxy the Milky Way is. Roughly the same age, roughly the same structural type, roughly the same range of stellar populations, roughly the same processes of star formation and evolution operating within its disk. When astronomers want to understand the Milky Way, which is difficult to study because we are embedded within it, unable to step outside and see our own galaxy's full structure. They often turn to Andromeda as the closest available analog. To look at Andromeda is, in a limited but genuine sense, to see something like what our own galaxy looks like from outside. We look at Andromeda and find not an alien other, but a relative, something different in detail, similar in kind and in that resemblance, something that quietly reinforces the sense that the universe is coherent, that the same physics, the same processes, the same story plays out again and again across billions of light-years of dark. There is something Andromeda has been doing continuously for the entire duration of human history that requires no instrument to appreciate. It has been sending us its light every second of every day, for the entire span of recorded civilization, for the entire span of the human species. Photons from Andromeda's trillion stars have been arriving at Earth. During every war, every celebration, every ordinary Tuesday evening, every moment of great joy and great grief that any human being has ever experienced, Andromeda has been quietly, continuously transmitting. Not a message, not a signal intended for us. Simply the ordinary radiation of a galaxy doing what galaxies do, burning its stars, emitting light in all directions, filling the surrounding space with photons that travel outward forever. Some of them reach us. They always have. They always will, for as long as our planet exists. The galaxy does not know we are here, and yet tonight, lying in the dark, you know it is there. That asymmetry, unreciprocated awareness, reaching outward into the dark, is perhaps the most human thing about looking at the sky. And so we close. Here, at the edge of everything, 2.5 million light-years away, Andromeda turns. Its spiral arms, slow and vast and patient, rotate at the same pace they have maintained for billions of years. Long before our sun ignited, long before the Earth cooled, long before the first creature on this planet looked up and noticed a faint smudge of light in the dark, and felt, perhaps, the first distant stirring of a question. It is still there. It has not changed on any time scale that matters to a human life. It will be there tomorrow night, and the night after that, and long after every human who has ever lived has been folded back into the matter from which we came. It is moving toward us, slowly, at 110 kilometers per second, which is fast by any ordinary measure, and glacially slow by the standards of the universe. In 4.5 billion years it will meet us, but that is not tonight's concern. Tonight your only task is to let the weight of your body be held by whatever surface lies beneath you. Let your breathing slow. Let the stars, the ones above you at this moment, the ones in Andromeda 2.5 million light-years away, occupy whatever quiet space remains between your thoughts. You are very small. The universe is very large, and somehow, improbably, beautifully, one of the universe's smallest and most temporary arrangements of matter has managed to understand something about the largest and most permanent things in existence. You looked up. That is enough. That has always been enough.